Hello, everybody. Welcome back. Today we're going to be covering Unit 8.9, which is about something called the Henderson-Hasselbalch equation. So you're going to need your calculator today and also have out your equation sheet as well. And let's get started. So let's just start off with reviewing what a buffer does. We talked about this in the last unit, but I want to just refresh your memory that the purpose of a buffer is to resist changes in pH. Okay, so whatever the system is, whether you're adding strong acid, strong base, doesn't matter, a buffer system will keep the pH nice and steady, which in our biological systems in our body is very, very good. So just to refresh your memory, okay, remember that there are two types of buffer systems. It's either a weak acid and its conjugate base are both present. And again, usually that conjugate base is going to be coming from a salt of some sort, an ionic compound. The other type of buffer is a weak base and its conjugate acid is also present. Again, that conjugate acid is likely coming from some sort of a salt. So what you've got in front of you here, I know this doesn't really look like it, but that acid right there, that is acetic acid, which is definitely one of our weak acids. And this compound might look a little strange, especially since it has the metal, the cation, written at the end. That looks odd. We're used to seeing the cations at the beginning of a formula. I don't know why it's written this way, but sometimes acetate compounds are written this way. This compound is sodium acetate. So if you think about it, what have we got here? We've got a weak acid, and we've got its conjugate base, the acetate ion, right there. This is a buffer system, okay, and we're going to talk about calculating how do you get the pH of a buffer system. We're going to talk about that today, but I'm just going to show you an example here. If this buffer system has a pH of 4.74 and it's maintaining that pH nice and steady, if we were to add some sodium hydroxide, which is one of our strong bases, look at what happens to the pH. It does go up, but only a very, very small amount. Okay, now the math associated, guys, with what happens to the pH of a system when you add acid or base to it, the math is not on the AP exam anymore. Writing the reactions is on the AP exam, and that's what we looked at in the last unit, is just what reaction occurs there. Okay, but all I'm trying to show you on this slide, guys, is just to reinforce the concept of what do buffers do. They keep the pH nice and steady. Now, on your equation sheet, ladies and gentlemen, if hopefully you have that nearby, okay, let me just show you where this is. There is an equation right here, okay? In this equilibrium section right here, towards the bottom of that section, there is an equation second from the bottom. That is called the Henderson-Hasselbalch equation, and that's what we're going to be talking about today. So I want you to be looking at that equation, and this is how it appears on your equation sheet. So I want to break it down for you. Okay, pH, obviously we know what pH is, but let's talk about what is this. We've briefly mentioned it, but I want to say it again. Remember that little lowercase p mathematically just means negative log of. So pKa is just the negative log of the Ka value. If you were to forget that, ladies and gentlemen, what pKa is, is written on your equation sheet right underneath this Henderson-Hasselbalch equation. Okay, which, by the way, since that name takes so long to say, I am from now on going to refer to it as the Hendy-Haas equation. Okay, it's just quicker to say. Now, what's going on there? Like, what do these things represent? Well, remember, guys, what a buffer is. And this is, and I should have said this at the beginning. The Henderson-Hasselbalch equation is only to be used if you are dealing with a buffer system. Let me say that again. That is really important, and I should have said that right off the bat. My apologies. The Henderson-Hasselbalch equation is only to be used if you are dealing with a buffer system. So in a buffer system, guys, you're going to have some kind of a weak acid and its conjugate base. Brackets mean molarity. Okay, so this part of the Henderson-Hasselbalch equation that's at the end, okay, this negative A over HA, it would be the molarity of your conjugate base divided by the molarity of your weak acid. Okay, and so I've sort of simplified it over here, base over acid. So look how convenient this is. Okay, this question says, calculate the pH of the following. 0.75 molar lactic acid, and then it gives us the Ka value for lactic acid, with 0.25 sodium lactate. Now, ladies and gentlemen, I recognize that this is a buffer system because here's a weak acid, and here is its conjugate base. As I said earlier, usually tied up in some sort of an ionic compound, a salt. But look how convenient this Henderson-Hasselbalch equation is. pH equals pKa, what is that? That is negative log of the Ka, which is 1.4 times 10 to the negative fourth, plus log of, now what's the conjugate base in this scenario? Well, that's right here. And what is its molarity? 0.25. So 0.25 molar over the molarity of the acid, which was 0.75 molar. Okay, let me grab my calculator and let's plug all of that in. And let's round that to 2 decimal places, 3.38. So that pH, ladies and gentlemen, is the pH that this particular buffer system is going to hold steady. This buffer system in this problem is going to hold a pH of around 3.38. It's going to keep it nice and steady there. Okay. Now, what if, let's see, let me erase all that. Okay. What if you're dealing with a buffer system like, I'm just going to make up some values, like 0.5 molar ammonia and 0.85 molar ammonium chloride. Okay, remember that another type of buffer system is a weak base, like ammonia, and its conjugate acid tied up in this salt. This is also a buffer system. So what do you do in this circumstance? Okay, I would say still pH equals pKa plus the log of, now in this case, and this is why I like to write it, sort of think of it like this, what is the base in this situation? In the problem that we just did here, the base was my conjugate base. But in this example that I'm doing here, here is the base. So I would say 0.50 molar base over acid. What's my acid? Well, in this case, it's a conjugate acid, but that's okay. It's still an acid nonetheless. And I would plug that in. So it doesn't matter if you're dealing with an acidic buffer system or a basic buffer system. If you think of the Henderson-Hasselbalch equation like this, I think it makes it a little bit easier. Okay. Now, in this particular example that I've given you with ammonia and ammonium chloride, you would likely be given, instead of being given a Ka value, you'd be given a Kb value. And we're going to talk in just a minute about, well, how do I get that Kb into a Ka? We're going to talk about that momentarily. Okay, now if you look at this Hendy-Haas equation here, and I want you to imagine that you're dealing with that lactic acid buffer system that we were just looking at a minute ago. And imagine that the molarity of the acid and its conjugate base are the same molarity. This fraction then is going to come out to be 1. And ladies and gentlemen, if you're familiar with logarithms, the logarithm of 1 is equal to 0. So this whole term is equal to 0. And what does that mean? That means that if you're dealing with a system which comes up where the acid and the conjugate base, or in the other type of buffer system, if the base and its conjugate acid are equal in their molarity, the pH will be equal to the pKa. Another thing you can tell from this equation, let's say you're given a problem, which I'm going to show you in just a minute, where you're given this and you're given that. Sometimes you will be asked questions like, if this is the pH and this is the pKa, which one of these species is in a greater concentration? Okay, you can solve for that ratio if you have this and you have this. Okay, that does come up. And I'm going to show you an example of a problem like that in just a second. So let's look at a question here. It says the table to the right shows the values of Ka for 4 different weak acids. Which of the following pairs of chemical species, when combined in, and this is important, equimolar amounts, that means same molarities, results in a buffer with a pH closest to 7.5? If you guys will recall, if we're dealing with buffers, we can use the Hendy-Haas equation. Oops, let's do it this way. Base over acid. Since it says that we're dealing with equimolar amounts, this whole term will equal 0. So essentially, I'm going to choose a buffer system whose pKa is closest to 7.5. Now, let's imagine this is a multiple choice question. You don't have a calculator. So you're looking at this column, which has Kas, and let's practice those estimating skills. Okay, when you take the negative log of a number in scientific notation, like this one, 4.0 times 10 to the negative 4th. Remember, the pKa of a Ka like that is going to be close to the exponent. The exponent is 4. Since the first term in that scientific notation is greater than 1.0, Okay, let me erase that. This guy's going to have a pKa of like 3 point something. Okay, so if I were to make a buffer system with this first acid, HNO2, with that acid and its conjugate base, I would get a pH of 3 point something. Well, that's not very close to 7.5. Look at the next acid. This is going to give me a pKa of 4 point something. That's not going to work. Look at the next one. This one's HClO. This is going to give me a pKa of 7 point something. Okay, that's promising. And then the last one is going to be 9 point something. All right, so I can tell that my answer, let me change to red here, is going to be this guy. Okay, hopefully you were able to eliminate answer choice A, because this combination, that's not a buffer system at all. HNO2 would have to be present with NO2 minus, its conjugate base. OH minus is not its conjugate base. So answer choice A, that's not even a buffer at all. B, C, and D are buffer systems, but C is our answer. Okay, so this is an example of a free response scenario, okay? And it kind of reviews things that we've done in the past few units. It also goes over some of the things that we have done, talked about today. So I want you to pause the video, read these questions very, very carefully, and see how you do. Give it a try. All right, let's see how you did. So first of all, guys, we're given in this problem, it says 1.2 molar NaOCl. That is a salt, okay? And it says that that salt is essentially going to break apart, because that's what ionic compounds do when you put them in water. They dissolve. And the OCl minus is kind of where we want to focus our attention. So OCl minus is going to react with the water to give us that reaction. So this is the reaction we're focusing our attention on, this what they call the hydrolysis reaction. So this first part says write the equilibrium constant expression for this hydrolysis reaction. So if you did it right, that's all you have to do. That's all you have to write to get full credit for part 1. Please notice that it says Kb, okay, in my expression, because, ladies and gentlemen, what is OCl minus? It is a base. And how did I know that? Because look at what it's doing from left to right. It is accepting a hydrogen ion. That means it is a base. So the equilibrium constant that I should write for part 1 is for a Kb value. Okay. And so in the next part, it says calculate the value of this Kb equilibrium constant. And you might say, well, how am I supposed to do that? If you look at the table on the right, we're only given Ka values. On your equation sheet, you have an equation that looks like that. Ka times Kb equals 1 times 10 to the negative 14th. If you know the Ka for a particular acid, which we do right here, you can solve for the Kb value of its conjugate base by using this equation that I've written in green. OCl minus is the conjugate base of HOCl. So the Ka for HOCl and the Kb for OCl minus are linked together in that equation. So plug in the value for Ka and solve for Kb. That's going to come in handy in the next part. Okay, so part 3 says calculate the value of OH minus in this solution. Okay, and this is my reaction. And a couple of units back, I introduced you to my little acronym. I call them WOMIX problems. Problems where the reaction is being reacted with water. We need an ice table that involves molarities. We're going to be adding and subtracting and solving for X. So I've written part 3 out on a separate page here. Let me get to it. And here it is. So I've used that hydrolysis reaction. I've set up my ice table, set up my KB expression, solved for X, and they asked us to solve for the molarity of OH minus. How did I know that X was in fact equal to OH minus? Because I've been very diligent in writing out my ice table. I know that these are the same thing. And that's what I get for X, which is my molarity of OH minus. Okay, so hopefully you did all right on letter C. Let's go ahead and look at letter D. All right, this time we're dealing with a buffer solution. Okay, and it says we have, again, that same salt, NaOCl, and HOCl. Okay, this is a buffer system because here's my weak acid, and here is its conjugate base. Those are the requirements to be a buffer system, and they've given us the pH. So part 1 says calculate the value of the hydronium ion concentration in this buffer solution. Guys, remember H3O plus and H plus represent the same thing. So all I had to do was use my regular old pH equation to solve for the hydrogen ion concentration or the hydronium ion concentration. Okay, now part 2 is going to pull something that we talked about today. It says indicate which of HOCl or OCl minus, the weak acid or its conjugate base, which one is present at a higher concentration in the buffer solution. Support your answer with a calculation. So because it's a buffer system, I'm going to use the Henderson-Hasselbalch equation, and there it is. Let's plug in the pieces that we know. We were given the pH. On the previous slide, we were given the Ka value for HOCl. pKa, remember, is negative log of that value. And it's this ratio right here that I don't know. So let's do a little algebra. Okay, I can get it down to the log of that base over acid ratio equals negative 0.6876. Let me move that out, down, okay. 10 to the power of, this is how we get rid of logarithms, 10 to the power of negative 0.6876 gives me this. Okay, so I can see that the ratio here of OCl minus to HOCl is less than 1. That means that the denominator is larger than the numerator. So I can answer this part 2 here that HOCl is in a greater concentration than OCl minus, and I've shown the math that proves that. So we've talked a little bit more about buffers and what they do. We've now brought in the math piece of this and how you can calculate the pH of a buffer system using that Henderson-Hasselbalch equation and seeing some of the sort of tweaks that you can use it, some other kinds of questions you could be asked using that as proof. So I hope you guys have learned a little something today, and I look forward to seeing you next time.